Today we're going to be learning about synchronous counters. However, before we begin talking about synchronous counters, I would like to review non-synchronous counters or asynchronous counters, because I find that if you understand non-synchronous counters, synchronous counters are actually so much easier. So we begin by noting that this counter that we have on my screen is non-synchronous. You can see that the clock source is triggering the first flip-flop. The first flip-flop is always connected JK to power, so it's toggling. It's acting as a frequency divider. And the output of the first flip-flop becomes the clock of the second one, and so on and so forth. And as you can see, the frequency is going to be divided every time. If I connect the 4-channel oscilloscope that I can find on my right screen over here, I just connected it and changed the colors of each of the wires so that on my screen I can see them in different colors. I can then open my oscilloscope, press play, and you can see the channels toggling on and off. Now, maybe it's easier if I put it in white. What I'm going to do is I'm going to change the scale to be, oh, let me start again. Let me press play again to make sure that my channels are turning on and off. There you go. So you can see that it is counting in binary. You can see, let me zoom out a little bit, or zoom in a little bit. You can see here how they're all 15 or 1 1 1 1, and then 0 0 0 0, and then 0 0 0 1, and then 0 0 1 0, which is a 2, and then a 2 and a 1, which is a 3, and then a 4, etc. So you can see it is counting in binary. Now there's one major flaw that asynchronous or non-synchronous counters have, and that's why it's called a ripple counter, because the problem is that the signal it takes time for the signal to propagate through every single flip-flop. If I had more flip-flops, more bits, this time it would be more propagation delay between the first flip-flop toggling and the last one. Now you can see it clearly if we zoom in, like at this point right here, when all flip-flops are supposed to turn off at the same time, you'll actually notice that that is not the case. Let me try to zoom in and not lose that little edge right here. I'm going to zoom in a little bit more. It's going to take a few times zooming in and recentering it before we can start seeing the discrepancy or the little flaw. It's not really a flaw, it's just a behavior that sometimes it's not desired. You can kind of start seeing it here, how the 4th bit is reacting a little bit later. There's a little delayed response. There we go. I think we've got it in this last frame. So if I stretch it, there it is. So if I were to visually just study it, it looks like they're all turning off at the same time, but there's actually a few nanoseconds delay. If I put my time markers, the time between the first flip-flop turning off or starting to turn off and the last one is in the 60s or so nanoseconds. I mean, between one bit and another is like 20 some nanoseconds. And it may not be a big deal. However, if we have a counter that is used for something very important, like I don't know, a medical device or something like that, then these are not going to be adequate. Let's say I'm having a laser eye surgery. I want to make sure that those numbers are accurate because I'm dealing with like very, very small numbers. So what we're going to learn today is how to make a counter that doesn't have this propagation delay issue that occurs with non-synchronous counters. Okay, so again, that was the point of reviewing that so that we understand the need for synchronous counters. So I'm going to build it side by side. Nope, I moved a little too much. I still need to refer to some of these components so that I don't take so long to copying and pasting. So what I'm going to do is I'm going to make what we call synchronous. Notice it's missing the prefix A, which means no. So for this counter, what I would like to do, and I'm going to use the same concept. So we're going to have my 1s place, my 4s place, etc. So here's going to be my 1s. Now I'm going to actually make a little bit more room because you're going to see that we're going to need a little bit more room between these flip-flops to show you how they work. Okay, and then this one's still going to be the 8s place, and then the 4s place, and the 2s place. Okay, so now the first thing you should realize to make counters that count synchronously is that I'm going to make a note down here. We have to connect the same clock source to all flip-flops. That's the key to making synchronous counters. Let me change the color so that it's obvious. Make it green. So this green clock, this green wire is going to go to every single flip-flop. That's going to ensure that it counts synchronously. There's no delay between the clock telling the first flip-flop to toggle or the last one. Now, at the moment, if I were to connect my outputs to a light to see what's happening, it's not counting. I think it should be very obvious that it's not counting. What do you think is going to happen? If your answer is that they're all going to toggle together, you're right. You can see that all the bits toggle together, and that's not really counting in binary. So what is it that we have to do? Well, we cannot connect the clock to the previous bit like we did for the ripple counters or the non-synchronous counters. So what we have to change is the time, or the when the JK is told to toggle. Now let's do a little exercise in counting in binary. I'm going to do a quick screen sketch right here. So when we count in binary, we have our 8s place, our 4s, our 2s, and our 1s. So we start by counting forward or up, and it looks like something like this, right? That's a 2, then a 3, 4, then it's a 5, and then a 4 and a 2 is a 6, a 7, 8, 9, and it keeps going. Okay, I'm not going to go all the way, but it keeps going. What I want you to notice is the pattern. Now, we already got the ones place to toggle. You can see here that the ones place is connected properly by toggling every single time it gets a falling edge. The issue now is, how do we get the twos place to toggle? Like, when should the twos place toggle? So I'm going to highlight at the location or the time that the twos place should toggle. What I want you to notice is what's happening in the ones place. So because they're going to be working at the same time, the two flip-flops toggled at the exact same time when the clock tells them to. So notice that the twos toggles when the ones place is a 1. So when the ones place is a 1, the twos place at the next edge of the clock, it should toggle. Do you notice that? Now, let me highlight in a different color. What is going on in the fours place? The four place toggles here and here. Now, what is going on? Well, it's not just that the twos place is a 1 like the previous example. What we notice is that both the 1s and the 2s are both 1. And then you can see the same effect in the 8s place. The 8s place toggle when all 3 previous bits are 1. It's kind of like counting in base 10 or in regular numbers. You count the next place value, it counts up when all the previous place values are already at 9999. So if all the previous bits are full, the next place value should count forward. So that's what we want to do. We want to check when the previous bit is a 1, and then we enable the next flip-flop to be ready to toggle. So let's do that. So here, what we're going to do is we're going to make it so that this one, the JK, need a 1 at both J and K, when this one is a 1. I think that's very straightforward. Right? We connect the JK when the ones place is a 1, the J and K is going to have a 1, and when the next time the clock says go, the JK is going to be ready to toggle in the twos place. Now, I'm only going to test the first 2, the last 2 are not connected at this time. So when this one's a 1, this twos toggles. Do you see that? So when the one place is on, the twos is ready to toggle. And that's how you get it to work. Now, how about the fourth place? If you recall, the fourth place should toggle when both the 2 and the 1 are both on. So what do you think we need to do? If your answer is an AND gate of the first and second bit, you're correct. So I'm going to place an AND gate. Let me see an 08. And the AND gate is going to go, I'll put it right here. It doesn't matter where you put it. Some people build these counters vertically. It's up to your layout preferences. So what I'm going to do is this AND gate is going to give a 1 to JK, making it ready to toggle when the 2's place is a 1 as well as when the ones place is a 1. So what we're going to see is when the ones place is on, the twos toggles now, and then when both of them are on, the fours place toggles now. What do you think about the eights place? For the eights place, we got to check when all 3 previous bits are on. Now, there's 2 ways to do that. Let me show you the long way and then the short way. I'm going to put a 3-input AND gate, which is the 74LS11. So when all 3 previous bits are on, so I have to use it, that's why I said I have to use a 3-input AND gate. There's a different way, let me show you. So it's this first one, then I'm going to check the twos place, and I'm also going to check that the ones place is on. So I check all 3 for this last one. And it's going to work, you can see, watch. When this one is on, the twos toggles. When the first 2, the fours toggles. And then when these are all on, now the eights toggles. And it's working, counting forward properly. All right. Now, some of you are probably thinking, well, the AND gate gets bigger and bigger and there's an easier way. And you're right, because if I had to add another place value, let's say I added the 16th place. I'm going to put it right there. If I added the next bit place value, I would have to check that all first 4 bits. So I need a bigger AND gate, and a bigger AND gate if I add more place values. But to get around it, instead of doing that, we're not going to use the triple AND gate. What we're going to do, and copy and paste this one, I'm just going to use a 2-input AND gate. And we're going to take advantage of the fact that this AND gate already checked the first 2 bits. So we check the fours place, and we piggyback from this one, because this one already checked the first 2, checked the ones and the twos. So this one is a result of the first 2 bits being on and the third one. And we do the same thing for the 16th place. Let me see if I can fit the AND gate. Oh, not quite. Let me move it a little bit to the right and then move the wire. So, wow, I moved quite a bit. I think it's fine. So now what's going to happen is the 16th place is going to toggle when all the previous ones, so the 8 as well as, and again I already checked the ones and twos here, and then with the 4, so I'm piggybacking from the previous one. And you'll see that if I press play, the pattern is going to continue. When the ones is 1, the twos toggles. When 2 and 1, the fours toggle. And when we have the fours, the 2 and the 1, the eights toggle. And when do you think the 16 is going to toggle? If your answer is when all previous 4, like now, it will toggle. There you go. So that's how you make a synchronous counter. The key is that you connect the clock source to all the flip-flops. After that, you connect the first flip-flop to toggle mode. So that one is the first one, and yeah, that one you have to connect power to both JK. That one is, you got to start somewhere. And then what I'm going to put is that the remaining or subsequent flip-flops connect to toggle mode when previous cues are, or previous cue bits are 1. Or another way of saying it is and all the cues. Okay? Now, there you go. I don't know if that note helps you. It usually helps me to make little notes like that when I'm learning a new process or a new counter or something like that. Now, how do we make this count in reverse or count down? So I should actually emphasize the fact that this is up or forward counting. Let me make a little bit of space and let me copy all of this. Oh, not the schematic, not the oscilloscope, just there. And I'm going to paste it down here so we can compare both to each other. Okay, so for counting down, my mouse is a little bit delayed, apologize. Okay, there we go. When we're counting down, what we're going to have to do is think about it in the other way. So actually, let me make a little space right here, and let's talk about what happens when we're counting down. Okay, so when we're counting down, we start with the 8s, 4s, 2s, and 1s. But now we start with all the bits being 1 for 15. And then we have a 14. And then we have a 13. And a 12. Is that right? Yeah, that's pretty good. And then an 11, which would be 8, a 2, and 1. And then a 10. A 9. An 8. I'm going a little bit sideways, but that's okay. I'm writing with my right hand on the screen. And then we have a 7. And then a 6, and so on and so forth. I think that's enough bits to capture the pattern. So what we see now is that the 2's bit toggles when the previous bit is a 0. You see that? So it toggles when the previous bit is a 0. The 1's place, it's going to toggle fine. It's the 2's place that we're looking at. And now for the 4's place, notice when it toggles here. And what's happening? If you said both previous bits are off or 0, you're right. And last but not least, what color is that? That's not very bright. I'll use green. The 8's place toggles when all 3 previous bits are 0. So it's the same concept as what we did with the counting forward, but instead of checking that they're 1, we have to check that they're 0s. So let's do that. Some of you may be thinking, oh, just put an AND gate or not AND gate. But that would not be right, because we're not checking that they're 1 and then inverting and giving JK a 0. We're not doing that. What we need to do is check that they're 0 and then ANDing. So it's kind of like a NOR, but that's not what we're going to do. So I think it's just easier just to add inverters or connect to the not Q's. So here, instead of connecting the remaining flip-flops to 1, what we're going to do is we're going to connect it to 0. So we're going to do it to the Q primes or the not Q's. I'm not sure if you call it not Q's or Q nots. Okay. Now, this is a little confusing here with the AND gate. So what I always suggest is for you to delete all the connections. So I'm going to delete those AND gates so that we don't get confused. So the only thing that we have is we have the clock to all of the clock inputs of my flip-flops. We have the first flip-flop to toggle mode. Now what we're going to do to make it count down or in reverse, we're going to make sure that JK have a 1 when the previous bit is off. Well, how do we get a 1 when it's a 0? If you said, yeah, connected to the not Q, you're right. Now there's supposed to be a little inverter symbol here that's not shown, but that's okay, it's a little bug. So now what I do is I check, okay, when this is a 0, the Q not or the not Q is going to have a 1, 1, making this one toggle. And look, it's going to be counting. I'm going to focus on the bottom one now. So right there. Okay, so if I press play, we'll see that my counter is counting. Ignore the other 3, just this one. So it's 0, and then 3, and then when this one turns off, the next one toggles showing a 1. 3, 2, 1, 0. 3, 2, 1, 0. So notice that the 2's toggles when the 1's is off. So it's off, now it's going to toggle. Okay, and then for the rest of them, we do it the same. Let me get an AND gate from up here. I'm going to grab one. Copy, paste. Okay, put it back so that I don't confuse you. So then what happens is now, to make this one, we need to give it a 1 when both of these are off. So we check that when the Q is off, the not Q is on. So this is what's going to give me my 1 that is needed for JK. So I checked that that one is off, as well as the previous one is off. And you can see that the 4th place is going to toggle when the first 2 are off. As now, the 4th is going to toggle. And there's a 3, 2, 1, 0. So it's counting. And we do the same thing for the rest of the bits. We connect the AND gate to check the previous bit is off, as well as the first 2. And we just piggyback like we did before. That one checks that one. I'm sorry, not that one, that one. The 8th place checks the result of the 4th. And then here, the 16th place is going to check the 8th place and the result of all the previous ones right there. It's kind of nice how it like lines up. Let me see if we make them all the same. There you go. So now I just keep repeating this pattern, and it just needs an AND gate in between each of the bits. And now you can see that this bottom counter, the difference between the bottom counter and the counter on counting forward is that we check that the previous Q's are a 0. not a 1. This one's counting forward, and the bottom one is counting in reverse. Now, if I were to put a oscilloscope like I did with my other counters, my non-synchronous counters, if I were to put an oscilloscope like I did with that one, you would notice that there's no propagation delay. All the flip-flops turn on and off exactly at the same time when they should. There's no 20 nanosecond delay or whatever it is that your flip-flop may be incurring. So there you go, just to highlight, the previous counters had one input clock going to the first one, and then the clock frequency got divided as it rippled through. And the JKs were always set to power. What we do differently for synchronous counters is that the clock is all coming from the exact same clock source, and what we do is we control when we have a 1-1 ready at JK for it to toggle. All right, thank you very much. Let me make sure. Yep, that's it. Have a good day.